Okay, so here's 3.2. A little bit longer lesson. We're likely going to break it up into 2 different days in class, and then I followed up with a worksheet day on top of it. Benton, go. Shorter worksheet though, okay? Just something to kind of get us some additional practice over this. So we have to go back to some of the old exponent properties that we talked about in chapter 2. So if you're not very confident with those, make sure you get back out. Ooh. Sorry, my dog just ran into a door. Make sure you get back out that sheet I gave you in chapter 2 that dealt with exponent properties and kind of practice with those a little bit more. So with this first one, we have 7 to the 1/4 times 7 to the half. So if we were to put these in radical form, meaning in their root, so a 4th root and a square root, we wouldn't be able to multiply them. Once we write them as a rational exponent, though, we can. So think about same bases. Okay, if you're multiplying 2 terms of the same base, you add their exponents. So we will be taking 7 to the 1/4 plus 1/2. So what do we know about adding exponents? If we want to add exponents, or not just add exponents, if we want to add any fractions together, they have to have what's called that common denominator. So I have to get a common denominator here in order to add these exponents and simplify this completely. So let's think. Between 1/4 and 1/2, what's our common denominator? Benton, what do you want? You want to say hi? Put your nose out here. You goofball. My dog's being very needy right now. I'm sorry. Hi, sweetheart. I'll play with you soon, okay? So again, sorry guys. If we want to add exponents here, we need to find that common denominator. Between 4 and 2, that common denominator can be as low as 4. So then we have to ask ourselves, it'll be 7 to the 1/4 plus, what times 2 will give us 4? So that number is 2. So we have to multiply both the top and the bottom of that fraction by 2. So 1 times 2 is 2. 2 times 2 is 4. Okay, so now we can go ahead and add. Benton, out. 7 to the 1/4 plus 2/4 will end up being 7. Stop it. 7 to, buddy, to the 3/4. Over this way. Okay, and that will be kind of a final answer. If we wanted to go ahead and write this as a radical, and I'm not telling you that you have to, but if you were, it would be 7 in a root 4, 3, right? Just from a little practice from last time then. All right, looking at the next example, we have different bases, so we cannot add their exponents, but they're all taken to the second power. So we have to think about everything within this exponent, or within these parentheses, has that exponent applied to it. So this is going to be 6 to the 1/2 times 2, right? Because exponent to an exponent means we multiply them. And then multiplied by 4 to the 1/3 times 2. All right, when we multiply a whole number by a fraction, you multiply that whole number by the numerator. So this will be 6 to the 2/2 times 4 to the 2/3. One last step we can take here is 2/2 is 1. So this is 6 times 4 to the 2/3. Or if you really wanted to keep simplifying, 6 times cube root of 4 squared, right? All right. Moving on to the next one. All of this work goes toward that top example. Okay. If we're dividing things of same bases, you can subtract their exponents. So again, if an exponent's not written, the assumption is it's a 1. So we will have 5 to the 1 minus 1/3. You don't even really have to make a common denominator here to know that 1 minus 1/3 would be 2/3, but we can, and it would be 5 to the 3 over 3, right? 3 over 3 is 1, minus 1 over 3, which equals 5 to the 2/3. Or write it in radical form, 5 squared in a cube root. All right, now we're going to work on simplifying radicals a little bit. So if you did some honors topics in the last section, section 1 actually, I think, not section 1, chapter 1, you would remember a little bit about this. So we can break up radicals through multiplication, just like we can combine them through multiplication. So this is a square root of 12. So I'm specifically wanting to think right now, what are the factors of 12 that in which one of those factors has a clean whole number square root? So we start thinking factors of 12, 1 and 12. 12 is not a square root. Not a perfect square. 6 and 2, neither of those work. What about 4 and 3 though? 3 does not give us a perfect square root, but 4 does. So I can break this up between square root of 4 times square root of 3. Okay, because 4 times 3 equals 12. We keep it in the same kind of root it already was. Square root of 4 is 2, right? So we have 2. Square root of 3 is not a whole number, so we leave that inside of that radical bar to get 2 root 3. So get 72 then. Square root of 72. So we start thinking, what are some factors of 72 that might work here? So we want to start thinking, I don't know, what can 72 be divided by? The first thing I think of when I think of 72 is that it's divisible by both 8 and 9. It's also going to be divisible by 2. That will be 36. Also divisible by 3, that's 24. What else is there? It's divisible by 4 as well. Okay, so you can just kind of start thinking of things in your head. So the way I kind of like to work with these is just go up the number line. So can 72 be divided by 2? Yeah, that would be 2 and 36. So then think, well, 36 has a whole number square root. So then start thinking about, okay, is it divisible by 3? Yes, that's 24, but neither 3 or 24 has a whole number square root. Is it divisible by 4? Yes, by 18, that's 18, but that would neither, or 4 has a whole number square root, but 18 does not. We want kind of the bigger number, essentially, to be the whole number square root. So 72 is not divisible by 5, but it would be by 6. It'd be 6 and 12. Trying to think, what else haven't we talked about? Not divisible by 7, right, but is by 8 and 9. So I want to try to go sometimes to the highest numbers I can think of. So right now that's 8 and 9. So I'm going to break this up by the square root of 9 times the square root of 8. So I chose these because 9 does have a whole number square root, and 8 and 9 are two really large multiples for this, factors for this. So square root of 9 is 3. So we will have 3 root 8. All right, so just like we can break it up to simplify it, we can also combine. So if you have the same number of a root, so they're both cube root, then you can multiply their insides. So it's going to remain a cube root, and we're going to multiply 12 times 18. Okay, that's going to give us 216. So when we get to this point, sometimes I like to have you check, is that a whole number cube root? If not, we'll leave it. But just like I showed you last time in your calculator, we're going to type in a 3, go to the math button, all the way down to that root button that pops us up a different kind of root. So it can be cube root of 216. We do in fact get a whole number, and that is 6. So I'm going to go ahead and put that down as the answer. Again, we're just simplifying here. Okay, just like we did up top, I want to break up 135, only this time it's a cube root of 135. So when I break this up, I want to have two numbers in which one of the numbers is an even cube, or not even, a whole number cube root. So cube roots, when you start thinking about them, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4, 64. 5 cubed, 125, and so on. So those are some kind of big numbers to kind of think about. So let's first try 8, okay, because that is the smallest number of a whole number cube root. So 135 is not evenly divisible by 8. So then we start with next 27, because 27 is 3 cubed. So we see is 135 divisible by 27, and it is. It's 5. So let's go ahead and go with that. We're going to break this up by 27 times 5. The cube root of 27 is 3. There is no whole number cube root for 5. So we leave that in its cube root and move on. Okay. This next topic is going to be called rationalizing the denominator. So when we rationalize the denominator, it's simply because you should never, ever, ever be taking a root of a denominator. Okay, that's like an illegal thing in math. It's like having 0 in your denominator. You just can't have it. So just like we can break up addition, we can break up division. So if you're taking a root of the entire fraction, you can break that up by taking the square root of the top over that root of the bottom. Break it up into two different radical bars. When we rationalize the denominator, it's by multiplying essentially by a funny looking 1. So you have a root over a root. The number that goes inside is whatever is in your denominator. So root 5 over root 5. And again, we can do this legally because root 5 over root 5 just equals 1. So we're not changing the value of it, we're just altering the way that it looks like. So again, same kind of root. You can multiply their insides. 2 times 5 is 10, so the square root of 10. 5 times 5, root 25. The square root of 25 is 5. So we leave it like that. Okay, the whole purpose was to get the root out of our denominator, and we did so we're good. Okay, just like the last time, we're going to break this up by the square root of 1 over the square root of 3 instead of the square root of 1/3. Rationalize the denominator by multiplying by root 3 over root 3. This will give us the square root of 1 times 3, which is 3, square root of 3 times 3, which is 9. Square root of 9 is 3, so we have root 3 over 3 as our final answer. All right, I have 2 more examples for you, and it's going to tie together a lot of the different things we've talked about today, and even some of the stuff we talked about last time. So when we want to simplify radicals, we essentially want to pull out everything that we possibly can. So the first kind of way that I like to do this is to rewrite it as a rational exponent. So I would take 4a squared b to the 4th c to the 5th, all to the power of 1 over 2. Okay, since all of these have different exponents, there's not like a overall exponent I can put up as my numerator, so it's just going to be 1. It was a square root, so 2 goes in my denominator. So we know that exponent properties say this 1/2 applies to the 4, the 2, the 4, and the 5. Okay? So this will now be 4 to the 1/2 a squared times 1/2 b to the 4th times 1/2 and c to the 5th times 1/2. And why am I multiplying exponents together? This is because when you take an exponent to an exponent, you end up multiplying those exponents together. Okay? So let's think about this one right here. 4 to the 1/2, I have nothing to multiply that by, so I'm going to rewrite it as a radical, which would be the square root of 4. A to the 2 times 1/2. So let's work that out over here. 2 times 1/2. Two different ways you can think about this. If you have a whole number that's the same as your denominator, they cancel to just give you the numerator. Another way would be if we did truly multiply these out, you multiply the whole number by the numerator. So it would be 2 over 2, which just simplifies down to 1. So 2 times 1/2 gives me a to the 1st. Okay? What about 4 times 1/2 then? That's 4 times 1/2, which gives me 4 over 2, which just equals 2. So I get b squared. Now over here, 5 times 1/2 will be c to the 5/2, right? Which essentially we could rewrite that instead of as a rational exponent as the square root of c to the 5th. Okay, so now we want to gather up all the things that have been put back into a radical and gather up the things that have not. So again, checking over, we have the square root of 4, a to the 1st, b squared, square root of c to the 5th. So can we simplify any of this further? Let's look at square root of 4. Square root of 4 is 2. So that part we can simplify further. A to the 1st we cannot, b to the 2nd we cannot, and square root of c to the 5th we cannot. So that would be my final answer. Okay, that's as simplified as we can go. So let's work the same kind of process with this last example. So rewrite it as 27 a squared x to the 6th all to the power of 1/3. So distribute this. 27 to the 1/3 a squared times 1/3 x to the 6th times 1/3. Okay, so 27 to the 1/3, we can just rewrite that as the cube root of 27. A to the 2 times 1/3 is 2/3, and then x to the 6 times 1/3 is x squared. Okay, cube root of 27 is 3. A to the 2/3 is still a rational exponent. So we have not achieved bringing that out. So we want to look for a whole number exponent. So x squared would come next. Since this was not able to be simplified, we put it back in a radical. Cube root of a squared. That would be the final answer. Okay, you have plenty more practice on this. Lots of different ways that we can kind of work with these. But we will have a worksheet over this to make sure that you're understanding it.